can be obtained. Okay, so generally for any type of analog circuit design, okay, we tend to vary only these five parameters. Okay, the resistors, inductors, capacitors, current, and voltage. Fine. Along with that, when you are talking about technology node, because nowadays almost all the design are based on, all the circuit design are based on some technology node. Okay, then length of the devices, width of the devices also come into picture, along with the drain current and the transconductance. So using these specifications, using the specification that we had been given, okay, using the unity gain bandwidth and the output load capacitance, okay, we are just figuring out the transconductance, okay, of a MOSFET, okay, of generic uh, for a NMOS transistor. Okay, so the transconductance formula to figure out, this is one of the formulas to figure out the transconductance of a MOSFET. Okay, 2 pi FUGB. Okay, so we characterize the NMOS transistor in order to obtain the VGS, okay, gate to source voltage, which is actually the input voltage, and the width. We only have the length of the device, but we don't have the width of the device. So we are going to figure out the width of the device along with the drain current by plotting the drain current and the transconductance. Okay, so what we did, we went on to run a parametric sweep, okay, parametric sweep, and we figured out the value of VGS for the respective transconductance of 630 microsiemens. Okay, and for that particular value of VGS, we figured out the drain current.
This is
Okay.
180 node nanometer technology, right?
Yes,
180
sir.
nanometer node. Yeah.
Yes, because that's what is given in the specification.
Right.
Okay. Yeah. So we obtained the drain current, okay, and those values were, just a second. So through the characterization of NMOS transistor, we got the value of gate to source voltage as 685 millivolt and the drain current value as 775 microamps. Okay, and we had considered the width of NMOS transistor to be 10 micrometer. Okay, now using these values, we have the value of drain current, and we also have one more parameter, that the output has a balanced voltage swing. Okay, so balanced voltage swing in the sense, okay, it is nothing, it is half that of the supply voltage, which is 1.65 volt. The supply voltage that is given for us is 3.3 volt. Okay, so the using these things we can calculate the drain resistor. Okay, so using Ohm's law, we got the value of drain resistor as 22 kilo ohm, right? And then what we did, we built a common source amplifier with a resistive load. Okay, so that's what we are going to showcase here. Okay, this is the common source amplifier with a resistive load. Okay, and what is the value of load resistance? That is 22k, we had just calculated. Okay, now if we plotted the gain of this particular amplifier, we had the gain to be around 22 dB. Okay, but the actual specification that we received from the market analyst is, we have to build an amplifier for a gain of 40 dB. Okay, now how can we improve the gain? Because here the gain is suppressed mainly because of this heavy load. Okay, heavy load of this drain resistance, which is this 22 kilo ohm resistor makes the design bulkier. Okay, so what we do is, we replace this with a constant current source. Okay, so this is how we replaced the drain resistor with the constant current source. We already have the value of drain current as 75 micro. Okay, and with this circuit, we got a gain of 49 dB, which is again 9 dB more than what we require. Okay, and practically there is one more thing. Practically, it is not possible to have a constant current source. We don't have a constant current source, right? And why is the gain getting shot up, okay, from 22 dB? Why is it rising to 49 dB? Because of the impedance that is provided by this constant current source, and it is not an ideal current source. This is not real, okay. This is available for simulation purpose, but ideally in the real world scenario, we don't have a constant current source, right? So we are just replacing this with a PMOS transistor. Okay, but now how to obtain the PMOS transistor? Okay, we are characterizing the device in the same manner as your NMOS transistor. Okay, just we have to keep in mind the polarities are just the opposite. Okay, so you can check out that from this connectivity. Okay, so we are connecting the negative terminal of a VGS to the gate. Okay, or we can do one more thing. We can connect this positive terminal and connect the negative terminal to ground. Okay, but whatever value you obtain, okay, that should be having a negative sign. Okay, so just the inverse of NMOS transistor. Okay, so by characterizing this PMOS transistor, what did we obtain? Just a second. By characterizing this PMOS transistor, okay, we obtained a bias voltage. Okay, bias voltage that we obtained was 728 millivolt with respect to this drain current of 75 microamps. When it comes to PMOS transistor, it will be minus 75 microamps, right? So using this, we got the bias voltage of 728 millivolt. But what would be the value of VGS for PMOS transistor? It is VDD minus the bias voltage. Okay, so we had it approximately around 2.572 volt. Okay, now and the width that we had selected is width of PMOS that we had selected is WP. Okay, WP is equal to, okay, 30 micrometer. Okay, 30 micrometer. Wn is 10 micrometer, Wb is 13 micrometer. Why is this? Because of mobility. Okay, because of the mobility of charge carriers, the ratio of the width of PMOS is twice or thrice than that of the width of NMOS. Okay, because holes, the in P-type MOSFET, holes are the majority carriers, and it needs some additional force in order to create, there is a requirement of an additional force to create a hole, right? So because of that, the mobility is also less when compared to electrons. So the width is taken as either twice or thrice than that of the NMOS transistor, and that is based on the mobility ratio, okay, of both the charge carriers. Okay, so by using this, okay, by using these calculations, we created a common source amplifier, okay, with PMOS load. Okay, with this we stopped, and we just obtained the gain of this common source amplifier to be 43 dB. Okay, and we cannot make it exactly 40 dB, but still it is somewhat closer. Okay, closer to what is expected out of a specification, out of the given specification. And while doing the layout, madam has actually requested me to take the participants, especially the students, through the fabrication process. Okay, so we'll start the session today with the fabrication and well fabrication process. Okay, and then we'll move on to current mirror. Okay, current mirror, and followed by that we'll go on to differential amplifier design, and followed by that we'll go on into a 7-pack operational amplifier. Okay, so let us move into today's session, right? So until this point, in case if you have any doubts, you can let me know, because even during the QA session yesterday, I didn't have any questions to be answered. Okay, so until this point, if you have any doubts, you can let me know.
Yes, so you may
Participants, if
start.
you have
You
any
may start.
questions, please
If they have
put the
any
question in the
question,
chat
please
box.
write on the chat box. Yes, yes. There is no question till now, so you write on the chat
Okay.
box. Okay.
They can directly ask, rather. I mean, the students
Yeah.
can directly ask. So then it will be more clarified for them. I mean,
The
Just
students
we'll
are
take 1 or 2 minutes for that.
yeah, students can directly ask the question if there is any doubt in your mind.
If there
Okay,
are
you
no
can proceed.
queries,
Yeah, okay,
if
if
there are
you
no
can
queries,
proceed,
then we'll move ahead.
then yeah, right.
Yeah, thank you. Today, based on Madam's request, let me take you through the fabrication process. Okay. Generally, when we are trying to concentrate on fabricating a CMOS device, okay, the base material is the most important one. Okay, so here we call the base as substrate, and we take it as a p-type material, which is more easily available. Okay, p-type materials are more easily available. Okay, and what we do is we just get an oxide layer over it. Okay, and this oxide process is done by using a high purity, highly pure oxygen and hydrogen, which are exposed to the furnace at a temperature of approximately 1000 degrees centigrade. Okay, all these fabrication process happen within a very close and secured system. Okay, secured environment, so that we don't have any dust particles at all. Okay, so even those small dust particles can cause a huge impact on the behavior of behavior of integrated circuits. Okay, so that's why we do everything in a very closed and secured environment. Okay, so after we have an oxide layer over your p substrate, okay, we place one more layer, okay, which acts as a protective layer, which protects the oxide. Okay, which protects the oxide layer, which is called a photoresist. Okay, and uh, s- this is sensitive to light. Okay, light or uv rays. Okay, so that when exposed to that, okay, it gets ruptured. Okay, and it clears off. Okay, now we expose this photoresist layer, okay, to uv rays. Okay, so that we diffuse. Okay, we are trying to diffuse an n-type material. Okay, an n-type material, for example, a well. Okay, a small tub like structure. Okay, a small vessel like, or a small tub like structure. Okay, which we can check out over here. Okay, this is the structure that we are trying to diffuse into the p-type material. Okay, so to expose or to eradicate the photoresist layer at the point where we are going to immerse that particular tub. Okay, we are just removing that. Okay, we are just rupturing that photoresist layer, and then we are removing the photoresist. Okay, after removing the photoresist, we are just removing the oxide layer by using an acidic solution, most probably a hydrofluoric acid. Okay, so I think if somebody has fabricated a PCB board, then they'll easily understand what are these processes. Okay, so when you're trying to design a PCB board, that is a single layer or a double layer PCB board, what you'll do, what will be the first process? Okay, if you visualize the PCB board, then the overall top surface will be covered. If you think of a single layer PCB board, then the overall surface will be covered with a copper. Okay, so what you do, you design the circuit on a spice tool. Okay, take a printout of that particular circuit on a label sheet. Okay, then you place that circuit over the copper surface. Okay, and use heat, okay, to get that printed. Okay, so that's what you are doing, you have done till now. Okay, you have immersed heat, printed that circuit on the copper surface. Okay, and then you are removing the unwanted copper surface. Okay, by just putting that by just immersing that PCB board on a solution of ferric chloride. Okay, so what happens, that ferric chloride removes, okay, removes. The process of removing is called etching. Okay, the ferric chloride solution removes the unwanted copper surface. Okay, and we just have that printed circuit alone. Okay, so that is the process we have done till now. We have just removed the oxide layer by using hydrofluoric acid. Okay, and then we remove the photoresist also, because that is acting as a protective layer for oxidation. Since we have removed the unwanted oxide layer, okay, we remove the photoresist also. Now we go for the diffusion process. Okay, we diffuse the n-type material, okay, within the p substrate. Okay, and once this diffusion is done, we remove that oxide layer also. Why do we have this oxide layer? Okay, it is not an unnecessary thing, right? Because when you try to diffuse a material, okay, within the p-type, with a diffuser material, okay, which is opposite to whatever you have, which is opposite to the base material, okay, then it should not get spread out, or it should not get sputtered, okay, over the entire surface. It should be only for a region of space, okay, for a fixed region of space. That is why we have, or we make use of some protective layers like oxide, photoresist, etc. Okay, in order to avoid spreading of that particular material or diffusion material to rest of the base, okay, rest of the p substrate material. Okay, once you have diffused the n-type material, okay, now you coat, okay, now you form a polysilicon over the p substrate. So why do we have a polysilicon? Wherever we require the gate terminal to be formed, okay, we induce the polysilicon material. Okay, and just between the substrate and the polysilicon, we have a thin gate oxide. Okay, and that helps in creating the channel, okay, for the transfer of charge carriers from the source to drain. Okay, so that is why we have a thin gate oxide material. And then we remove the unwanted polysilicon again. Okay, we remove the unwanted polysilicon by the same etching process, very same etching process. Okay, so once that is done, again we mask the gate with oxide. Okay, we implant an oxidation layer. Okay, because that acts as a that acts like a mask. Okay, it prevents the other rest of the surface from getting spoiled or from getting diffused by alternative materials. Okay, so that it, because the main purpose is whatever we create, it should act as a MOSFET. Okay, if if those unwanted material gets split up or gets spread across the rest of the substrate, okay, then it acts as some other devices, maybe as a BJT or maybe as a resistor or maybe as a capacitor. Okay, so that is the purpose of oxidation layer. Okay, and once that is done, okay,
Hello, hello. Is it audible?
yes, yes,
Yes, I think sir,
and once
network
that is
is.
done, hello.
It
Please,
is
sir,
not
continue,
audible.
sir.
Yeah,
Till
yeah.
now it is. Some problem may be there.
Okay.
Transmission problem.
Am I
Sir,
clear?
voice, yes, it is
Yes,
breaking,
Yeah,
it
sir.
is.
yeah.
Just a
You are
second, just a
audible.
second. Hello, am I clear now?
Yes. Yes.
Yeah, yeah,
Okay,
it's
yes,
okay.
sir.
But the thing is, the same slide is there.
Yes, yes, I haven't changed the slide. It is step 12, right? Step 12 you are able to see, right?
Yes, Naveen.
Hello.
Yes, yes, step 20.
Yeah. Okay. I have not changed the slide. Okay. I'm just explaining those things. Okay. So sorry for the inconvenience. I slightly have some network issues. So hope it is getting resolved. Okay. So I've now switched off to another network. Okay. So now hopefully there won't be any issues. uh, yes, let us move on. Okay, so by using these masks, okay, we are trying to induce, okay, other type of material so that you can check out. Okay, just on either side of gate you have the drain and source, okay, which is of the alternative material when compared to the p substrate. Okay, and in case of PMOS it will be uh, in case of NMOS, it will be an N-type material, a P-type material, right? Okay, so we are working on that kind of process. Okay, and then followed by that, after you induce those required layers, okay, for which will help you in having source and drain. Okay, you remove that oxide layer again. So what do we see now? Okay, the gate, okay, and on either side of the gate you have the N-type material, and similarly in case of PMOS, okay, you use thick field oxide. Okay,
Hello,
and similarly in case
hello,
of
hello.
PMOS, okay, you use a thick field oxide. Yes.
Yeah, there is
Hello.
a kind of, yeah,
Hello.
there is a kind
Am I
of,
audible?
yeah. Now it's right. I mean, it's now okay. Hello, hello.
Hello. Hello, sir.
Yes, sir, you're audible, sir.
Yeah, yeah. Now it's okay.
I
Right. In between,
Okay. Okay.
in between, there
I
was
think
a
there is some network
fluctuation.
connectivity problem.
Yeah,
So
yeah.
please continue, sir.
Okay. Yeah. Yeah. Sure. Okay, so after we induce the type of material required to get a drain and source created in case of both NMOS and PMOS transistors, we again coat the top surface with a thick field oxide. Okay, so that it is not getting removed. It's not going to be removed further. Okay, because we are going to place get a metal surface. Okay,
Hello,
and
Mr. Navin. I have a query.
yes, sir.
For
Yes, sir.
in case of NOL, there is
Yeah.
only drain. Where is the source? Or there is a source. Where is the drain? Drain is not there. In
See,
case of NOL.
you have both the things over here. You can see here.
Oh, oh,
Let
okay,
me
okay.
point out.
Oh, that is
You have it here. Okay.
that is guard ring, right?
Yeah.
That one in plus, right, right. Okay.
Yes. Okay. Here it is just an N plus surface. Okay. In order to get here, you have the P type material for substrate of our bulk connectivity. Okay. Yeah.
Right, right,
So
right.
after getting these things, okay, after you form these things, okay, you again create a thick oxide layer, because after this you'll be getting your contact points, right? So for getting these things, you are just inducing a thick oxide. Okay, over that thick oxide you get the aluminum. Okay, aluminum on that material. Okay, uh, after coating the top surface with aluminum, we remove the unwanted things, because we tend to include the metal contacts, right? So for that purpose we tend to remove the excess metal. Okay, wherever we want the aluminum we have it. Okay, other than the other than those locations we remove the metal. Okay, we remove the aluminum material, and then
The brown one
fill
is
up
polysilicon, right? Brown one.
brown one here, whatever you are seeing
No, no,
here.
no, no, not here. I mean,
Okay.
on top of that, in the gate region, for gate contact, there is a polysilicon, right?
Yes, yes, exactly.
Right.
Yes. Okay, so now you fill up those vacant spaces with the metal. Okay, metal contact. Okay, so after you fill up those things, okay, you tend to uh, name those terminals, okay, as gate, drain, source, and bulk, and this is how it looks finally. Okay, so now when you move into layout, okay, you have different types of layers, right? And it depends on the technology, no particular fabrication unit. Okay, certain fabrication unit, they don't have any order in which you need to get the layers. Okay, but certain fabrication unit, they'll have a specific order, like first you need to place the substrate, and then you should place the oxide, then you have to go for metal, or then you'll have to start with contact. Okay, so they'll be having an order in which you'll have to create the layers. Okay, so it depends on fabrication unit or the foundry from where you procure the particular technology node or technology library. Okay, so this is about the fabrication process as of how the PMOS and NMOS devices are getting created. Okay, so any doubts till now?
Anyone?
No, no.
Anyone?
Any doubts in the fabrication process?
Any student or any attendees have any doubt? You can ask it.
So when you start VLSI design, when you start learning about VLSI design, this is the basic
Right.
that you should
Right.
have an idea of. Okay, how
Right.
we fabricate a device.
Right. This is the
Okay,
basic idea you
yeah.
should have. Right.
So shall we move on? In case if
Yes,
you don't
please.
have
Yeah.
Yes,
any,
Sure.
please.
Yeah.
yeah,
Sure. Sure.
sure. Thank you. So now let us move into today's we move towards some complex circuit. Okay, we'll not have an additional source. Okay, in order to bias your devices. Okay, instead of having an additional source, we'll have some additional circuitry. Okay, which doesn't damage or which doesn't alter the purpose of your design. Okay, instead it takes care of the currents and voltages that are required for each and every block or each and every device, okay, to turn on or turn off at a particular point of time. Okay, that is the purpose of bias voltage, right? So how to generate those things, okay, using a circuitry. Okay, and current mirror does that part, okay, in a more efficient manner. Okay, and what is the purpose of current mirror? To copy a reference current. Okay, to copy a current from reference source to a terminal. Okay, to one more terminal. Okay, for a MOSFET it is a drain current. Okay, so that is what. Okay, here for a MOSFET, the drain current is a function of the gate to source voltage. Okay, as we have seen here. So the transistor is biased at the reference current. Okay, they produce a VGS. Okay, and that voltage is applied to the gate terminal of another MOSFET. Okay, this is the theoretical behavior. Just have a look at this statement and let us see how it is created. Okay, so here you have a reference voltage, reference current. Okay, and you have the gate to source voltage over here. Okay, this is getting copied to the other side of the device. So current or voltage that is getting generated by using this device, okay, is getting copied to the circuitry, rest of the circuitry. Okay, how is it done? Okay, that is experienced over here. Okay, the current, let us talk about the current in both the transistors. You have two transistors, right, M1 and M2. Okay, so the reference current here is 1 by 2 mu n C ox W by L VGS minus VTH, because the device has to be in saturation. Okay, and the same thing is getting copied to the output. Okay, iout is also say has the same current. So that ratio, okay, ratio of the output current to the reference current is given by this equation. We are not going deep into the equation. Okay, but if you wish to have an idea about how we arrive at this equation, so you can refer Design of Analog CMOS Integrated Circuits by Bezar Razavi. Okay, we have taken all the circuits, model circuits, and the equations. We are just demonstrating whatever is there in that book. Okay, because that is what is expected, right? So whatever is there in the textbook.
So we have to change
Yes.
the only the MOSFET width rather than length. I mean, length should be matched for both the transistors. So just
Yeah,
we can change
length will remain constant always.
constant.
Okay,
Right.
length will
So
always remain constant.
we should
It will
change the
be,
width.
yes.
Right.
Uh, just you can think about a simple inverter. Okay, so if you talk about an inverter, you have many aspects to be discussed in an inverter. Okay, so you'll be having a fast inverter, you'll be having a slower inverter. Okay, so how to differentiate a faster inverter and slower inverter? How when a device acts faster when the width is more. Okay, when the width is more, the charge carries, it has the
It's
opportunity of
deter. It will be determined by RC time constant. I mean,
RC
that
time
is
constant, that is fine. Okay, when we are talking about the MOSFETs,
right.
okay, so it will be mostly dependent on the width, okay, width of the device.
I mean, R will change depending on the width. Also, C will change. I mean, area will change. So depending on the width, so C will change automatically. So
Exactly, exactly.
RC will change.
Okay, so it is also dependent on RC time constant. But since we are talking about width and length here in in these topics or in these sessions, I'm just concentrating on those aspects alone. Okay. Yeah. If you try to just for an inverter, just try to vary the width of the devices and check its behavior. What happens to the delay and what happens to the RC time constant? How faster or how slower it's reacting to those changes? Then you'll get an idea of why why these equations are getting involved when we are discussing about current mirror. Okay.
So
So
M1 will
now,
act as diode, right?
sorry, sir.
M1 will act as diode.
Yes, it is diode connected. When you try
Right.
to connect the gate and the drain of a
Right.
MOSFET, then it is obviously a diode. It acts as a
Right.
diode.
Right.
Okay. So now let us try to demonstrate this simulation, this current mirror circuit. Let us see how it behaves, how long it copies. Okay. So let us move into the tool part. Okay. So let me close all these things. Okay. So I'll circuit view. Name the cell as current mirror. Okay. So I'll select OK, right? I'll make use of the NMOS transistors. Okay, just I'll take a look, take the same default length and width of the device. Okay, so followed by that, you can also rotate this. Okay, you can just flip it sideways. Okay, in order to rotate this device. If you, I'll just show you how to do that. Okay, just if I'm placing the MOSFET here, okay, and if you try, okay, you can see, right, it should be just flipped out. Okay, by checking out this circuit. Okay, it is connected back to back, both the gates are getting connected, right? So if you are trying to make this type of a connection, okay, you need not look, sorry, able to see my screen
No, no, your screen is not visible.
now, sir?
No, started sharing. Now it's okay.
Yeah,
Right.
okay,
Yes, sir. Now
okay,
it is.
fine. So here in this circuit, you can visualize both the gates of the transistors are connected. Okay, so that is the device is connected back to back. Okay, so that you can note down the drain, sorry, source terminals have to be grounded. Okay, it acts as a common term. So here, how to make these type of connections in cadence. Okay, in the Virtuoso tool. Okay, so if you select the device and if you try to rotate it, okay, if you go for rotate option R, okay, it will rotate the entire symbol. Okay, it will rotate the entire symbol, and what happens finally, it will be placed like this. So note down here, the source comes at the top of the device, okay, and not at the bottom. Okay, the source and drain have to be flipped here in the symbol. Okay, to avoid this kind of confusion, what you can do is you can just flip it sideways just before placing itself, because when you get on the right hand side, you can see the device how it looks like. Okay, so if you go for sideways, okay, then you get the flipped version of NMOS transistor. Okay, so I'll go to hide and place the device now. Okay, I need a source, okay, constant DC voltage source in order to turn on my device. Okay, turn on or turn off my device. So I'll go into analog lib. Okay, so I'll go for VDC, and here the supply voltage I'll take is 3.3 volts. Okay, so I'll go for hide, and I'll have it over here. Okay, and then I have a constant current source. Okay, a constant current source. Fine, we'll just have it here, and another constant voltage source in order to plot or in order to verify whatever we are getting. Okay, are we getting the required voltage or current at the other end? Okay, so that is a variable. I don't know what is going to be the value. Okay, so I'll just place it over here. Okay, now I need certain ground terminals. I need some ground terminals. Okay, so I'll search for G and D, right? So I'll have it over here. Fine. Now let us do the connectivity. Okay, using wires. Okay, so I'll complete this part right now. Okay, and here I make the connections. And here this part is getting diode connected, right? So I'll do that, right? And then the drain of this device is getting connected here. Okay, and rest of the connections. Fine. Now the bulk of NMOS transistors are getting connected to the drain. Okay, that is the most negative terminal. Fine. The circuit is now complete. Okay, I'll check and save the circuit so I don't have any errors. So I'll run the simulation. I'll go for launch ADEL. Okay, so I'll set up the simulator. Okay, it is already Spectre, no issues. And then the model libraries, you can see all the three model libraries are selected.
I have a query.
Yes, sir.
The current source will be remain there as a current source, or it will be replaced by a saturated PMOS.
It will remain there. The current source will remain there.
So will you will not
Here,
you will not
here
replace.
we are not designing a common source amplifier. It is a current source,
It,
right?
it's
We are trying to bias
it's fluctuating actually.
the device, or we are.
Right.
Hello.
Yeah. Hello.
Go ahead, sir. Go ahead. You are trying to ask something.
No, no. So current source will remain say, there. I mean, you will not replace the current source with the help of PMOS. I mean,
No, that is in terms of the amplifier design.
right,
How the common source amplifier evolved over the years.
right, right. Now,
How it began.
since PMOS can be used as a current source in its saturation mode,
Yeah.
so that's why I'm asking that whether we can replace the current source with the PMOS.
I'll show that in future. Okay, as we
Right,
move on to the amplifier design, differential amplifier and operational amplifier, I'll
right,
show how it happens.
right,
This is about a current mirror circuit. Why are we
right,
making use of those connections in the differential amplifier and operational amplifier? What is the purpose and what is the application? Okay, so that is why we are going through this design.
right, right.
Okay,
Sure.
yeah. So here I'll go for the nominal processing corner, and we have an unknown variable, right? So I'll just mention the value. Okay, I'll just assume a value. Okay, and then I'll go for a DC sweep. Okay, save DC operating point. Okay, and go for component parameter. Go for select component and select the DC voltage source which has the unknown variable. Okay, and select the component that has to be swept. Okay, DC voltage. Select OK. Again, come back and mention the sweep range as, sorry, you start from 0 volt and you go on up to 3.3 volt. Okay, just apply and select OK. And here you have to note down one more thing. Okay, I am going to outputs. I need to set up the plots, right? So go for setup from design. Okay, in order to plot the current, okay, for a circuit, you need to click on these terminals. Okay, in order to plot the current, you need to click on these terminals. For example, I am selecting the drain terminal for both these MOSFETs. Okay, and if you wish to plot the voltages, then you need to select the nets, as we had done for the amplifiers earlier, amplifiers and NAND gate earlier. Okay, so it's up to you to decide, okay, whether you wanted to plot a current or you wanted to plot the voltage, okay, of the devices. Okay, just keep this in mind. If you are plotting a current, then you'll have to select the terminals. If you're plotting the voltages, then you'll have to select the nets. Okay, so now select OK, and you can see here, okay, you have selected the drain terminals of the devices. Okay, now let us run the simulation. I'll go for simulation and select netlist and run. Okay, so sorry, I have an issue here. Uh, Okay, I haven't mentioned the value of current, I guess. Yes, the DC current value I haven't mentioned. Okay, so let us assume the current value to be 30 microamps. Okay, and check what is happening. Okay, so now I'll save the circuit.
So the current source, the current value of the current source should match the current of the drain current of
Yes,
the.
drain current at the output. Okay,
That is the
so
saturation. Right.
yes.
Right.
Now let us simulate this. So yes, now we have got it. Okay, so let us hope the waveforms are visible, right? So let me change the width also. Okay, so you can note down here, okay, the current remains at 30 microampere only for a fraction of second. Okay, only for a fraction of a second it remains at 30 microampere, and then it starts increasing exponentially. Okay, so and you need the current to be at the same level as your input for an extended period of time. Okay, just for a fraction of second it gives 30 microampere, then there is no necessity of having this current mirror, right? So what we do is we include one more stage. Okay, so including one more stage suppresses it. Okay, so let us see how that happens. Okay, so first let us see the theoretical part.
Since it is a current source, so
Yes.
we should get the constant value of the current, right? So
Yes, that's what we are getting, the constant value only for a fraction of second.
right, right,
Okay, let us see how to make it remain constant for an extended period of time.
right, right.
Okay, so uh, okay, so this is for the current mirror, normal current mirror, and just when we are trying to include, okay, and why is this happening? Because of the channel length modulation effect. Okay, this effect happens because of the channel length modulation effect. Okay, and so what shall we do? The VB can be chosen. Okay, VB can be chosen in such a way that Vy is equal to Vx. Okay, voltage at this point, the diode connected point, is the same as the voltage at the output. Okay, so how can this be obtained? Okay, by including one more stage, okay, in total. Okay, one more stage at the top, so that it is getting suppressed. Okay, and so that it is available, this constant current is available for an extended period of time. Okay, by including one more stage. Okay, so let us see how to do that. Okay, so I am closing this. So I'll save the state.
Can you please show your slide? Right.
Yes, sir. Yes.
Slide.
Yes.
Your slide. I want to see your slide. The second
Uh,
one.
just a second.
The cascode current mirror.
Yeah. Is it visible now?
Yeah, it's okay.
Yes, sir. Yes. You have any doubts here, sir?
Yeah, the what is the role here for M0 diode or M0 shorted MOSFET?
So what we are trying to do here is we are trying to have the current, okay, remain at the same level for an extended period of time.
Right,
Okay, it is not remaining in such a manner because of this channel length modulation effect.
right,
Okay, so to avoid that, what we are trying to do is we include one more transistor. Okay, and in order to make it constant, okay, we should have Vy is equal to Vx. The voltage at the
right,
drain
right.
diode connected
So,
end should be the same at the other end also.
so that we should get the same current.
Yes, yes,
Right,
exactly. Okay, so in order to do that, what we are doing is we are we are getting it by including one more device, okay, that is diode connected. Okay, and
right.
let us see how this is done.
So, what is the role of this diode?
uh, Role of this diode is to suppress it, okay, in order to avoid it in increasing exponentially.
Oh, right, right, right. This is one current mirror, and
Yes,
this is one. The apart part is on another current mirror, right?
yes, same circuit getting connected in series
So
like that.
all the devices
Cascoded.
aspect ratio same. I mean, or
Same.
all the devices M0,
Yeah.
M1, M right,
Yes, same.
right, right.
Okay, so let us move into the cascode current mirror part. Okay, so you can even copy the same thing. Okay, so I am copying the same circuit. Okay, so I'll go for copy and just rename it as cascode current mirror. So in order to avoid consuming more time, I'm just copying the circuit. Okay, so now let me open the circuit, right? So I'll just include one more stage of NMOS transistor over here. You can just copy the devices also. So how to copy it? So select the NMOS transistors, okay, and use the shortcut C. Okay, C for copy. Okay, just click on C. Just before that, let me remove this net. Okay, so I select the devices. Okay, I select the NMOS transistors. Use the bind key C. Okay, C to copy the devices once again. Okay, right. Now let us do the connection. Use the wire. Okay, get one more current mirror. Okay, cascode the current mirror. Get diode connected. Done. Okay, and then the bulk connectivity. Okay, done. Now check and save the circuit. Okay, check and save the circuit. Run the simulation. We have already saved the state, so I'll just load that state. Okay, now I'll just run the simulation once again. So now the outputs are at a different transistors. So I'll go for outputs setup. From the design, I'll choose the drain of NM3 and drain of NM4. Okay, so just select OK and now run the simulation. Right, so now you can see it is remaining at 30 microamps for an extended period of time. It remains constant, right? And
Right.
even if it increases, it's not there is no too much of difference. It is almost constant.
It will be independent. It should be independent of voltage.
Yeah, exactly.
Right.
Okay, so it remains at 30 microamps for an extended period of time. So what is the application of this? Okay, when you talk about some bigger circuits like a differential amplifier or an operational amplifier, a 7-pack, a 30-pack, or a 50-pack amplifier design. Okay, so in order to avoid external voltage sources coming into picture, okay, we create the sources within the circuitry itself so that it is self-sufficient. Okay, so that your devices are self-sufficient. So I'll close this. Let us move into the next part. Okay, after we complete the cascode current mirror part. Okay, where are these things going to be applicable? Why are we learning about these current mirrors? Okay, so let us move into that aspect. Okay, so next we are moving into the differential amplifier. So what is a differential amplifier? An a circuit that amplifies the difference between two voltages. Okay, the circuit that is used to amplify the differences between two voltages. Okay, and there are two types which are single-ended and double-ended. Okay, single-ended differential amplifier and double-ended differential amplifier. So what is the significance of those circuits, those type of circuits? Okay, if we have two differential outputs. Okay, so one is at signal low and the other one is at signal high, and are electrically floating with respect to the analog ground. Okay, whereas in single ended, okay, there is no common mode range. Okay, because one of them is diode connected. Uh, we implement current mirror over there. Okay, so differential inputs provide more stable reading, okay, when EMI is present, and therefore it is recommended to use them whenever noise is generally a problem. Okay, whenever we have noise as one of the external effects that is causing some issues in your circuit, you can go for the differential ended inputs, differential ended circuit. And in case if you are looking for a cost effective circuit, okay, if you are looking for a cost effective circuit, and if you are trying to reduce the number of wiring, external wiring and internal wiring, then you can go for the single ended input. And the main advantage of having a single ended input is you'll have a higher gain, okay, when compared to the double ended circuit. Okay, and that is why we go for a single-ended differential amplifier, and this is the type of circuit that we are going to have a look at. Okay, in order to obtain the voltage transfer characteristic, okay, load of the differential amplifier must be defined. Okay, and here we select a current mirror load. Okay, current mirror load. Let us see how to implement this circuit. Okay, and we have already uh, uh, s- calculated or obtained the value of width for NMOS and PMOS transistor as we had done it in common source amplifier. So if you just look at this circuit, okay, it is two stages of common source amplifier connected back to back. Okay, so you can see you have a PMOS transistor, you have an NMOS transistor, and here you have PMOS and NMOS transistor. So the devices are connected back to back. Okay, and here you have one more transistor, okay, which is called a tail transistor, which takes care of the biasing part.
So this
Okay,
will, I have a suggestion. This
yes sir,
M1 and M2 will act as a differential amplifier, right? I
yes,
mean,
differential input.
differential input.
Yeah,
And the upper two transistors, M3 and M4,
yes,
that will act as a current mirror load,
yeah,
right?
exactly.
And the lower one, M5, will act as a current source, right?
It will act as a biasing circuit.
Current source will not be there in the
uh,
differential
we
amplifier.
it takes care of current source will be there, but main aspect of this circuitry is biasing. Actually
Yeah.
we can make use of a current source also.
Yes, I think here
Okay,
the
current
NMOS
source.
has been used as a current source. I think so. I
Current,
don't.
is
Yeah,
it current biasing
exactly.
or voltage biasing? That is stated.
Yeah,
The bias
exactly.
is connected to, yes.
No, no, biased is voltage bias, but I think it is a current source.
Current
Uh,
sourcing or sinking, because it is biasing means
I
generally
mean
differential of a,
current sinking, right? Current sinking.
Yes, exactly. Exactly. Okay, so let us see how to do that. Okay. Right. So let us see how to get the differential amplifier, and it can also be called as a 5-pack operational amplifier. Okay. So let us see how to do that. Uh, okay. So I have created a self view. Okay. I'll get an NMOS transistor. Okay, from GPDK 180. Okay, the length already we have seen. Okay, 1 micrometer, and width we have already calculated as 10 micron. Okay, just whatever we have obtained for a common source amplifier, I'll take those things. Okay, and here one more transistor, I'll just flip it off. Okay, so length is 1 micron and width is 10 micron. I'll just flip it sideways. Okay, so you can see the view over here.
Navin, Mr. Navin,
Yes, sir. Yes, sir.
I have one more query. The
Yeah,
current mirror which you have used as load, I mean the upper part of the circuit, that is been implemented by PMOS or NMOS?
PMOS transistor.
PMOS.
Yeah.
Right. Right.
So I'll click on hide and place it over here. Okay, so NMOS part is done, and I have one more tail transistor. Okay, so the length here is going to be 1 micron, and width is going to be 40 micron. Okay, these were already done, okay, by using the device characterization, as we already performed it for the NMOS transistor. Okay, we have already we are taking the same aspects. Okay, so I'll rotate it sideways at this 1 micron and width is 40. So click on hide, place it here. Okay, so NMOS part is done. So now we'll move into the MOS. Okay, so the length of PMOS transistor is again 1 micrometer, and width we have considered as 30 micron. Okay, so I'll go for hide and place the device. Okay, so now I'll flip. Okay, on the other side I'll flip the device sideways, where the length is again 1 micrometer and width is 30 micrometer. Okay, play. Okay, and then we need the sources, right? So let us go for the analog lib library. Okay, where VDC is the constant voltage source, and
I, I
for sub. Yes, sir.
I have a query. I mean, since it is PMOS, that's why it's the width is 30 micrometer. Otherwise, it will be identical to the NMOS. I mean, if it was it will be 10 NMOS, then it will the width will be 10 micrometer, right?
Yeah, and you can decide. You can
I mean,
work on it.
all the four transistors should have aspect. If those are same types, so should have same aspect ratio, identical.
Not
Since
necessary. Not
right,
necessarily.
okay.
Okay,
So
that dep. Yeah.
bottom two have should have same I mean identical W by L aspect ratio, and the upper two, I mean the which we use a current mirror,
Okay.
should have identical aspect ratio, right? So
Uh,
now since it is PMOS, that's why we are just having the width three times of the NMOS.
yes,
30
that
micron.
is one of the reasons. And
Right,
here we are just making use of the common source amplifier that we had designed earlier.
right.
Okay, so
So
there in
that
that common source amplifier, what was the dimensions of PMOS and NMOS transistors? Length were
current,
same, 1
right,
micron.
right.
Width of PMOS was 30 micron, and width of NMOS was 10 micron.
So that current will remain same. Current will
Yes,
remain same. Right,
exactly.
right.
Okay. that is why we have a differential input and differential pair, right?
Right.
And we have two modes of connectivity,
Right.
single-ended and double-ended. Okay, so supply voltage is 3.3 volts. So I'll get it here. And the bias voltage is, as we have already calculated, it is 685 millivolts for NMOS pair. Okay, it is 685 millivolts. Okay, and I'll give a sinusoidal input source. Okay, so both of them are 180-degree out of phase. Okay, let us see how to do that part. Okay, so I'll take V sine, the sinusoidal voltage source, and I am taking the AC magnitude to be 1 volt. Okay, amplitude, let us mention 10 micron. Okay, and frequency 10k, right? So I'll place it over here. Okay, but for the other one, okay, so I'll take AC magnitude as 1 volt, same thing, amplitude 10 micron, and a frequency to be 10k. Okay, and I'll just rotate it. Okay, so that it is 180-degree out of phase. Okay, sorry. Mm, 1 volt, 10 micron, and 10k. So I'm just rotating it. Okay, so that it is 180-degree out of phase. Okay, and I need one more voltage source for the tail transistor, where I give the voltage for the tail transistor, bias voltage for the tail transistor. Okay, which we have characterized as 600 millivolt. Okay, so I am getting it over here. Done. So now let us complete the connection. We need the ground terminals. Okay, so in analog lab I'll look for ground, and let us complete this.
So, I would interrupt Mr. Naveen a bit.
Yes, sir.
Actually, we have a limited time up to 6:10, right?
Yeah.
So then we have to leave this platform, this Zoom platform. So since it is a registered platform to our university,
No issues. I'll try to complete it as soon as possible, sir. No
right? So
issues. Yeah.
maximum time you can take up to 6:10, right?
Okay, fine.
Right.
Thanks for your intimation, sir.
Okay. Okay. Right.
Okay, so we'll complete the connection. So here we have the bias voltage for uh, both the sinusoidal voltage sources. Okay, and here it is for the tail transistor. Done. So we connected. So these are the differential pair. Okay, this is the differential pair. The bulk terminals are getting connected to the ground, or you can have a separate ground terminal also, not an issue. Okay, so I have the gate transistor, so gates of the device is connected. This is the diode connectivity. So both the sources are connected to each other, and the bulk terminals are connected to the most positive terminal. Okay, and what is left out is the output pin. Okay, output port. I'll go for add pin option, and I'll name the port as v underscore out. Fine, so I'll place it over here. Now labeling the nets is left out, So I'll go for labeling option and VDD V in 1. We have two inputs. Sorry, excuse me. So we have two inputs. So we name it as V in 1 and V in 2, right? And then we have the bias voltage for the tail transistor. So I name it as VT bias. So click on hide and I'll place them like this. Okay. Now label the terminals and circuit also. VDD, V in 1, V in 2, and VT bias. Okay. So we'll go to this part, VDD, one of the inputs V in 1, the other input VD, V in 2, and VT bias. Okay. So the schematic is now done. So this is your differential amplifier, 5-pack differential amplifier. Check and save the circuit. Okay, so we don't have any errors. So just we'll run the simulation. We'll go for launch ADEL. Okay, we'll set up the simulator. Okay, which is Spectre, and set up the model libraries. Processing corner that we are going to make use of is nominal processing corner. Okay, we don't have any unknown variables. Okay, so we'll choose the analysis that are to be performed. Okay, so transient analysis to check out the response of the circuit. Okay, so it will be at the stop time is going to be 500 microseconds. Okay, and I'll go for moderate accuracy default. And then I'll run an AC analysis to check out the gain of the circuit, and it'll be from 1 to 10 gigahertz. Okay, sweep type, let me go with the logarithmic sweep, and points per decade is going to be 10. So select OK, right? So now we get the analysis mapped over here. And now we'll set up the terminals between which we are about to perform these analysis. So I'll go for output, setup, from design. I'll select the terminals, V in 1, V in 2, and the output, right? And then let us run the simulation. So I'll go for simulation and go for netlist and run. Okay. Yes. So we can go for split all strips. Okay, select this particular graph and go for graph and select split all strips so that you can check out the response. This is V in 1, V in 2, and your output. Okay, now we need to plot the gain of the circuit, right? So I'll go for ADEL, direct plot, AC magnitude and phase. Select the output net, okay, and go for escape in order to get the gain of your device. So you can see dV20, right? So that gives the gain of your circuit, which is 47 dB. Okay, so here we have the gain as
From where you have selected the magnitude and gain?
so from the ADEL window, okay, from
Right.
where you run the simulation. Okay, so you have to go to results. From that you'll have to go for direct plot, and under that you can select AC magnitude and phase.
Right.
Okay, as
Okay.
soon as you select it, it will take you back to the schematic. So select the output net because you are just checking these things at the output, right? So select the output net and click on escape. Okay, select the output net, click on escape so that you get the uh, magnitude and phase. Okay, AC magnitude and phase,
So it will be gain
and
and
gain
phase
in dB,
or gain
gain
and
in
dB.
dB,
Right.
especially gain in dB.
Right.
So whatever you have seen earlier, okay, is also gain, but in terms of voltages.
Right.
Okay, gain in the sense you look for dB values, right?
Gain unitless gain. Right. That one.
Yeah.
And this is in
Yes.
dB. Right.
Yes. Even you can take that and convert it to dB. You can get, you'll be getting the same
Yeah.
value.
Log of that one. Right.
Yes, log of that.
Yeah. So I have one query. Can you switch on to your schematic?
Yes, sir. Yes.
Yeah. can I, instead of having a BT bias, separate BT bias, can I just
Okay.
bias? Oh, this BT bias, how much is this one? 100 millivolt. BT bias, the value of BT
600,
bias?
600 millivolts.
600 millivolt, right.
600
So
millivolts.
can I just, instead of
So instead of,
having a BT bias, just I can connect VDD and having a voltage divider, I can give it to this current sink or current source, whatever you say. So shall it be possible?
yeah, you
Or
can try that.
then
Yeah, you can try that.
then
Or you
instead
can
of,
have a,
yeah, yeah, then instead of going for two voltage source, we can have a one DC voltage source that will be sufficient for this one.
yeah, exactly. Exactly. Or you can go for a current mirror. That will also be a good option.
Oh, right,
Instead
right.
of this VT bias, you can implement a diode connected transistor on the other end. Okay, and that gives you the current mirror.
Right, right. Sure.
Even that serves, that gives you the bias voltage required for the circuit.
Right,
Current sink.
right.
Okay.
Hello.
Sure.
Yes.
Yes. Actually, apart from finding the gain from the DC response, am I required to find the delay from the transient response? I mean, is it necessary?
In case if you are asked to get, or if you are asked to obtain the delay from transient analysis, you'll have to.
So, can you just show once? I mean, how we can find the delay from using the transient response?
Yeah, I can show that. Okay. So already I have demonstrated this in yesterday's session also, but let me show it once again. No issues. Okay, so what you can do is go for tools and open calculator. Okay, so clear buffer and stack. Okay, so you are getting everything from the waveforms, right? You are getting the data from waveform. So just above keypad, you have a wave option. Okay, so enable wave option. Okay, and in function panel, okay, you can see delay, or you can search for delay. You have a search option. You can search for delay, right? So select delay, and here you'll be asked to select the signals. Okay, what is going to be your signal 1 and what is going to be your signal 2? Okay, signal 1, let me choose the input, one of the inputs, for example B in 1, and signal 2, let me use the output, right? Okay, and now you'll have to mention the threshold. Okay, threshold in the sense it is obviously going to be VDD by 2. Okay, but here you should mention the value that lies within the range of your signal. Okay, so it can be 685 millivolt. Okay, 685 millivolt, or and even at the output you'll have to mention that particular voltage, like 2.645 or something like that. Okay,
Need to
so
mention
what
the
I'll
peak
do is,
values.
sorry.
So I just need to find the peak values, right?
Yes, it should be on the positive potential. Okay, it should be it should lie within the range. Okay, wherever you have your sinusoidal, okay, it lies between 2.6475 and 2.6425 approximately. Okay, that threshold value should lie within this range. Okay, understood, sir?
Yes. Yes. Okay. Fine. Yeah.
Yeah. Okay, fine. So what I'll do here is, so I'll go back to this one. So threshold value 1, I'll mention it as 685 millivolts. Okay, and threshold value 2, I'll take it as 2.645. Okay, and edge type, edge number, you can select as you are looking for, whether you are looking for the propagation delay. In case of propagation delay, you'll have to choose TPHL and TPLH, right? So for TPHL, okay, you have to choose the input as falling, the output has to be rising. Sorry, input has to be rising and the output has to be falling, TPHL. And TPLH, it is just the opposite. Okay, or if you are looking for a generalized value, you can select either. Okay, so you'll be getting a delay value. Okay, so and edge number you can choose. Okay, so select apply. Once you have chosen everything, select apply, select OK. You have two options of evaluating the uh, expression. Okay, this is an expression, right? So you have two options for evaluating the expression. One is just evaluate the buffer and display the results in the buffer window itself. This is a buffer tab. And the other one is display it in a tabular column. So let us see how it looks like. Okay, so it is, you have a negative delay minus 49 microseconds. Okay, so this is to get it in a tabular column. Okay, and if you wish to check the delay here itself, then you can go for the other option so that you'll get it here itself. That's it. Okay, yes. So we have now gone through the feedback differential amplifier. Okay, now let us move into the next part. Okay, so let me check out. Sorry. Okay, so followed by cascade current mirror. Okay, we have checked out the differential amplifier. Okay, so let us move into the next one, how to implement. Okay, so you have designed a common source amplifier and you have designed a differential amplifier. Now combine these two. Okay, and you can create or you can build an operational amplifier so that whatever you have as a five pack differential amplifier will act as the differential mode. Okay, or will produce a differential gain. Okay, and whatever you have, the other one, the next part, okay, is a common source amplifier which induces, which is called as a gain stage. Okay, the first one will be called as a differential stage and the other one will be called as the gain stage. Okay, so that's what is given here. So basic two-stage common mode CMOS op-amp is a workhorse for many moderate performance analog applications. So this is mainly for circuits that are required to perform in an average manner. Okay, where we don't require higher gain. Okay, high gain as the throughput. Okay, or output. Okay, and this is highly reliable. This circuit is highly reliable. Okay, and you can look at the input stage where high input resistance is there to avoid signal loss. Okay, and you have a good amount of voltage gain. So for the differential input you had the gain as 47 dB. Okay, and the same way at the second stage. Okay, at the uh, output stage. Okay, we
Mr.
have
Naveen,
the shifting of DC level.
hello.
Yes sir, yes.
Can we have
Yes.
the layout of those basic amplifiers? What we have done? I mean, the differential and the those
Yeah,
things.
tomorrow
If
layout will be demonstrated tomorrow.
tomorrow, right? All the amplifiers. Otherwise,
Yeah, tomorrow.
it would
Yeah,
be
yeah.
it would be better if you demonstrate the layout along with the schematic, so that we can otherwise, I mean, going all the amplifiers and then going the layout of all amplifiers, that will be a bit, I mean, inconvenient for us. So I mean, part by part, I think it would be
So
better.
even if we part by part.
Right. Whatever
Okay.
the differential
Mm,
amplifier you have done, so we
okay.
can go through the layout of differential amplifier current source, and then we can go
So
to
it will time. I don't think time will be sufficient because you told me like it will
so
be until 6:10, right?
so you are going to have op amp today?
Yeah, operational amplifier will complete because we have time only for that. Okay,
Right,
tomorrow
right,
we'll
right.
take
Okay.
anyway. We'll take the circuit individually, common source amplifiers individually, operational amplifier differentially, operational amplifier as well as differential amplifier. Individual
Right.
circuits will be taken, and the layout will be demonstrated.
Since today's session has been started from 9:45,
Okay.
so almost it's of 9 hour session. So yeah, 9 hour
Okay.
30.
Okay. Okay.
Almost it's of 8 hour session, 8 hour 30 minute session. So
Okay.
it's
Okay.
a
Okay.
bit quite this thing. So you can complete.
Yeah.
So Okay, you can complete the op-amp schematic and then we can go for the layout tomorrow.
Yeah, because that's why we planned to complete the schematic today, because layout itself, we need a minimum time of half an hour to 45 minutes to complete the layout.
Right. So tomorrow you are going to give the
Yeah,
lecture on first half or second half?
no idea. Actually, the time slot is the same thing, 4 p.m. to 6 p.m.
Uh, uh,
So preferably it will be the same time slot.
Dr. Das Sarkar, is going to give lecture tomorrow on first half or second half?
So
No
actually,
idea, sir.
we
I don't have any idea.
you
Hello.
in our team,
Hello.
FDP team, would like to request you tomorrow, if possible, please take the session in the morning session in the first half. So
Morning
Uh,
session
s-
in the sense, what will be the timing,
you
sir?
no, I am
renowned
saying,
professor,
sir, I am,
your renowned
yeah,
professor.
Hello, hello. Yes,
Yes,
yeah.
ma'am. Yes.
actually my keyboard is not working. I don't know why false is going on sometimes. So I cannot open, but I am hearing that you are telling. Okay, so that the thing is, today we have to close, and actually tomorrow you are mentioning Rajavi, and one of our resource person who is fortunately the student of Rajavi, and he has actually he's in Kharagpur IIT, and today we have got one session from him,
Okay.
and yes,
I,
and tomorrow he would like to have a session, but the thing is his class lectures are actually in the morning session, and one of
Okay.
the important thing is if we set him in the afternoon, so
Okay.
your session we are not getting properly. So in that case,
mm,
what we can do, that
Okay.
if you are taking the session in the morning, so
Okay.
it would be very better, it would be better for
uh,
us, and will be like very much like can hear from you, so that really we can understand the whole thing what you are we are delivering for us. So
Uh,
tomorrow I think you will be talking of, I am hearing that you are telling about common source amplifier and others, and layout extraction will be there. For that you are telling that layout
layout part for all the three amplifiers: common source, differential, and operational
yeah,
amplifier.
from the schematics. Okay.
actually, what I suggest that since Vibhu sir is taking the design of all those cascaded amplifiers and all those things, so I suggest that the basic things, whatever here he's, Mr. Naveen is delivering the lecture on and showing us the layout and all those things, we should have those in the first half so that we can go through the Vibhu sir's lecture quite conveniently in the second half, since it's a quite big topic.
That is another issue. You just I am explaining what is the problem. Everyone is parallelly going on, so that we can have different different approach, and different kind of approach, as well as the basics to advanced level, and layout design actually we are having from Damodaran also on the yesterday session, but unfortunately I don't know whether they are whether he is not turned up, I don't know. So in that case I have communicated again today to Integral, if we have some layout session from you or Namodara, I don't know that who will be giving the session,
It's there
taking the
tomorrow,
session.
ma'am.
So tomorrow,
Tomorrow.
if it is the morning session, you will be giving layout, or Damodara will be giving the layout?
We'll be taking care of. We'll be taking care of.
You will be taking care of.
Yeah.
Yes. So in that case,
I,
can you accommodate it in the first session, that maybe you are telling to, we can start from 10:30 also, no problem.
so your so the slot will be between 10:30 a.m. To 12:30 noon, right?
Yes.
So let me check for the availability, ma'am, because we have
Even from 10 also, we can start from 10 also, no problem.
other assignments also that is planned along the same time. So
TKB
let us
sir.
check.
Yes.
And we'll get back to you, ma'am.
So it is very urgent. So if you can get back by like 10 to 15 minutes, it will be, you discuss, and I have communicated also to Rakesh also. Okay,
Okay, okay.
or
Let me check,
earlier.
ma'am.
Yes,
Let me
yes.
check and get back to you.
Yes, yes.
Okay.
Thank you then. Thanks once again that you are giving so much, like in detail, the things that you have described. It is really be helpful for the students as well as the faculty members. So if you are giving the lectures for tomorrow, the in detail layout and design rules, then it will be really for helpful for us that we are able to think, the students are able to learn, because layout is easier than any kind of things, and it is the step where we can extract the other things also. So it will be better if you give the session, if you take the session on layout and
Yeah.
on the design aspects that you were telling, and the layout also, and the thing that if the placement and routing you wants to talk about, then it will be it will be good. So you please make us understand that in which topic you are going to discuss, and if morning session, then we can accommodate all the persons, because you know that as these are happening in a in a manner that academics is also required as well as the everything. So we are actually, as we are from microelectronics and VLSI technology, the background physics and technology process we are learning also, and in the classroom session.
Okay, okay.
So if we can accommodate all the things, then it will be the complete picture the students can get. So
Okay,
if you
sure.
help in that way, so it will be really be helpful for us. So in
Yeah,
that
yeah,
case, you
sure,
just
sure.
okay. And any question, students, if you have any questions, and faculty members, if you have any questions to Naveen and his team, so please ask. Please ask in the chat box. You can write also.
So, Mr. Naveen, you are going to
Yes,
give the schematic of, I mean, the schematic of op amp tomorrow, right? And then,
If possible, I have already captured it. If you want me to just present, because right now almost all the participants should be having an idea of how to capture a schematic, right? So how to
Yes,
give the length and
yes,
width of
yes.
the
okay, okay, you can do
devices.
it. But you
So
have to
just,
complete it by 10 minutes. I mean, 6:10 up to 10,
yeah,
6:10.
yeah, no issues. It is
Right,
done already. So I'll just project it. Okay,
right,
project
right,
it for your view.
right.
Okay, so this is the this template that we are going to in which we are going to build the operational amplifier. Okay, so differential stage will be the input stage, and the common source stage will be the output. Okay, so let us see how it happens. Okay, so this is your differential stage, right? So with this, at the output, you are just going to remove this output port. Okay, and you are going to connect the common source stage. Okay, so I'll just open the common source stage also. Okay, so this is your common source amplifier. So you'll be combining both of these things, except for the sources. Okay, leave out the sources. And other than the sources, you are going to merge both of these things. Okay, let us. It look like this. Okay, so this is how it looks like. Okay, a 7-pack operational amplifier. So this part, okay, this part will be your differential stage, okay, or the input stage, okay, and this part will be your common source, okay, output stage, or you call it as the gain stage, okay. So together it is called as 7-pack operational amplifier, mainly because you have 7 transistors, okay, that is the reason. Okay, since you have 7 transistors, it is called 7-pack operational amplifier. And even this, okay, your differential stage, okay, you have 5 transistors, right? So it is also called as a 5-pack op amp. Okay, so that's it. So now we'll have
So,
to just
so,
run the
so
simulation.
this is
Yes,
one op amp, and this five pack op amp is a differential amplifier is one op amp, and this is I believe whole 7 pack is another op amp, right? Those two are
yes,
two
yes.
different, right?
This is also called as an op amp. This is not exactly the operational amplifier.
Right, right. This is
Also
differential.
called as, yes,
Yeah,
this is
this is
differential.
differential, and that is common source,
Yeah.
right? And the output will be connected to PMOS. I mean the load, right?
Yes, the output of this differential stage
Will
this
connect
differential stage will be
will be
connected to the
load
this
PMOS.
load.
Right.
Okay, so that's what we have done here. So
And
this the output of this differential stage is getting connected to the PMOS.
right. And the NMOS
Okay,
will be getting connected to VT bias. Right.
yeah.
Okay.
Okay, so I have just highlighted that connection. Okay,
Right.
so this is how. Okay, so now you can just run the simulation and check for the gain. So it should be,
So this is a
what should
five
be the
pack.
gain now?
This is a five pack different op amp differential amplifier, and this is a seven pack, right? So what is the
This is
benefit
7
of
pack.
what is the benefit of adding common source stage at the output of the differential amplifier?
It is not the benefit. This is in order, see, you have already built a differential amplifier. You
Right.
have a common source amplifier.
Right. Right.
Okay, so you are uh, building an operational amplifier
Right.
using the differential stage and the gain stage. Common source amplifier is also called as a gain stage amplifier, right?
Okay, for the
Single
for
stage.
right, I got it. So this is the output signal whatever I got from I will get from differential stage, that
Yes,
will be amplified by this common source, and it will be
exactly,
right,
exactly.
right.
So what should be the output gain? That
That
is
is
my
the
other
amplifier.
question. That is the
Right,
question.
right,
Okay, so you have connected two amplifiers. Okay, now what will be the gain at the output?
right.
It should be the sum of both the things, right?
Both
Both the
the things.
amplifiers.
Right, right,
Okay,
right,
so at the common source, you got a gain of approximately 43 dB.
right.
Okay, and here for the differential stage, it was around 47 dB.
49 or 47, right?
Okay, so 47 or 49, I don't remember. Okay,
49,
so it should be
right.
the sum of both these gains.
92 dB.
It should be approximately somewhere close to 90.
Right.
Okay, so with that, we'll close today's session. In case if
Could
you
you
have any.
please show us the waveform? I mean, the these things.
Yeah, definitely, definitely, sir, definitely.
Right.
So I'll go for the simulation process. I have already saved that state. So I'll load it. Okay.
It should
So
be
I'll just run the simulation.
yeah, it should be amplified than that of differential stage.
Exactly.
So gain, if I got the gain thing, so it will be 90 dB.
Yeah.
Right.
So this is how your input and output waveforms look like as a result of a transient analysis. So now let me plot the gain for your circuit. Okay, so results, direct plot, AC magnitude and phase. So at this stage, the overall output stage, okay, so let me take this to a separate window in order to give you a clear idea. I'll split the graph also. So this is the gain in 20 dB. So
Right.
you can see it is 91 dB.
91 dB. Right.
Okay.
Right. Sure.
Yes. So
Okay. Thank you so much for your presentation.
yes, sir. Yes.
It will be very
Thank
helpful
you.
for
Thank you very
us
much.
for designing these analogs, basic analogs, building blocks, and then for
Exactly,
our
sir.
students
Exactly.
also, for our postgraduate students also.
Yes.
So, thank you very much for this session. Right.
Yes, sir. Thank you.
So you should confirm when you are going to take the lecture tomorrow. I mean, should
Yes, sir. Just give me some 10 to 15 minutes time. So
right,
I'll check
Yes,
with
yes,
my team and I'll.
yes, yes.
right, sure.
Thank you all. Thanks for your patience.
Yes,
In
yes.
case if
Thank
you
you.
have any queries,
Thanks a lot. Yes,
you
we will
can
be
let me
coming.
know.